Okay, so you guys can start when you're ready.
Yeah, okay, so the lecture of Fast.AI this week is mainly about like LSTM and some of the revision of CNN and ResNets. And LSTM and CNN are already like talked about for a lot in the previous lectures. So today we will just like cover some of the key concepts of the, and the main part will be ResNet, which will later be covered by Dingfeng. And I'll pass time to Selwyn to talk about like LSTM and extensions of Ireland. Yeah.
So we already learned about the RNN. So the goal is to keep some information from the previous state in each cell to have a history. But it has some limitation. So if you don't want to have an extensive number of layers, and so we have to restrict it. So at the beginning, so we have some mini batches. So we divide the whole data set in the mini batches. But the problem is that when we pass from one batch to the next one, so we forget the activation functions. And one way is to have a huge number of layers, but then you have problem of the memory. So to have a good traceback, we can have a trade-off of remembering the previous steps and forgetting a part of it. So for example, from the video, so in a text where you have at the beginning of a paragraph, you have I'm from France, and at the end you want to predict I speak French. You need to remember from the very beginning, but most of the time, because you only have a few states in your neural network, then you cannot remember the beginning of the text. So one proposition is long short-term memory. So in that case, so each cell remembers, and we take the previous steps and we combine the previous step with the current step and the input to have this memory. So in each cell state, you have a gate that combine the input and the previous state, and we have this sigmoid function to let pass more or less the values that we take as input or from the previous step. So 0, we don't take anything, and 1 we take the whole value. And so the first, so we have four parts in this cell. And the first one is how much we forget from the previous state. So because you have the input and you have the previous output, and by combining them, you have with a dot product, you will have a value that is like, so if you predicted the wrong character, then the dot product will be very low. So you will have a value that is close to a 0. So you will not take this value. So you will not combine the previous state that you have from the cell. But if your prediction was good, then you will have a value that is higher. So you will take the previous step. So it's to balance how much from the previous step you remember, if your prediction was good or not. Any question? That's it. Not sure.
You guys are all so quiet.
Maybe it's not so clear. I don't know. Then the next part is how much we update the new state value. We have a time function. So that's like how much from the input we attack for the new state. and that's the addition of the output. So with all these steps, we combine it to have a good trade-off of the new input, the previous state, and the new prediction.
Yeah, and the new prediction here will be like taken into the next node to see whether the prediction fits the next input or not. If it fits, then it will be what will happen will be like the same with what happens in this node. If it fits, it means like we are the cell, we are using a good cell, then we are most likely to keep most of it, and the value here will, the value at ft will be always close to 1. And if the ht doesn't fit the next input, then the value close to 0. It means we tend to forget a lot of things because they are not like generating the promising result. Yeah.
You guys all concur with that? Okay. Go on.
Yeah. So there has been some other improvement, let's say. What is using Fast.AI is a GRU, so Gated Recurrent unit. So basically, it combines both the input and the forget gate into the update gate. So for the computation, it's easier and faster, and the results are better. To be honest, I cannot explain why, how, but I just.
How about the rest of you? Can you help explain why this architecture might be better than general LSTM? What's the key difference?
It's more messy. You have more lines.
You have more lines. Lines mean what? It's more complicated. More parameters.
More links. It's more linked.
More linkages.
More general that you can cross.
Okay. Anyone else have anything else to say? You guys should actually be able to tell the difference between the GRU and LSTM. After watching the lectures or reading a little bit. I mean, I know a lot of them, people say, yeah, just don't use the RNN, use an LSTM or GRU, right? And they usually perform comparably, but there are some differences. Which one has more parameters? LSTM. Do we all agree with that? Can you show us where the differences in the number of parameters are?
Yeah. Like the simulates the tangents and like you combine it. But
where do we need our W matrices? Right, because we're learning parameters, right, for the model. We all know about overfitting and underfitting, right? Underfitting is almost never a problem in neural networks, right? Okay, because you have just too many things to fiddle with. Right? Like my son, he's 7 years old. He likes to touch everything, like anything on the table he'll touch. So imagine like this my boy goes into a neural network. Wow, thousands, a huge panel of control dials to turn, right? So a lot of things to play with, right? So we are looking here specifically at the W matrices, right? Because those are the things that you need to tune. Because then the other operations are fixed. You're just varying those parameters. So where are all the W matrices in LSTM and GRU? I mean, you can look at the formulas. Where are the formulas for these things? Here's one, right? There's a weight matrix for the forget, right? It's a weight matrix for the input. There was another one on the other side. There's two there, right?
Yeah.
What's C?
the state.
The state?
Yes, the cell, the cell state.
Yeah, that's the selection, I think, right? Selection
Yeah.
gate. Okay. Yeah. 1, 2, 3, 3 weight matrices. And 4 is for the output.
Yeah.
Right? So we have 4 large W matrices in LSTM.
And in GRU we have
1, 2, 3. Slightly less complicated, right? More lines, yes, the architecture is more complicated, but less parameters because you are basically saying, I'm going to get the same functionality by squishing two things together, right? Can you imagine, like, for example, a sedan versus a coupe, right? You have 2 doors versus 4 doors. It's not like you cannot get into the back seat in a 2-door car. You just have to move the seats forward and then you can get in, okay? So it's the same thing here, right? You're getting away with fewer weight matrices because they serve additional functionality, right? You can think of it that way. So we're trading the number of parameters, the number of knobs that you can turn for a more complicated architecture where there are more shared parameters, right? And this is the whole story that you see over and over again in neural network architectures. You want to get away with more prior knowledge and modeling so that you don't have to go to that terrible, terrible overfitting problem of having a fully connected network, right? When you look at the fully connected deep neural network, you have parameters everywhere, right? You saw that in some of the, I don't know, VGG and other networks that came before AlexNet. They have all these fully connected FC layers at the end where the number of parameters like blows up to millions, right? Very, very bad. Great for learning any function you want, but really, really bad for estimating unless you're Google, right? Google has lots of data, no problem, okay? But you who are a graduate student at NUS, you don't have data, okay? So you cannot get away with such architectures, right? So in the CNN, we saw this before, right? How did CNN tie the things down so we don't have so many parameters? This is lesson 1. Come on, guys.
Yeah.
The same filter, so the filters have the same weights. When the filter moves the same way.
Right. Even though we're going on different parts of the image, it's the same W that's being applied for every filter. Oh, granted, we might have several different filters, right? We saw those pictures where every filter is a separate picture, right? Basically looking at different detectors. But that same 5x5, 3x3, or a dilated 3x3, whatever you want, is being applied to every part of the image. So you're only learning one set of weights for each filter. Well, that's not so terrible, right? Okay, maybe I'm learning 9 weights or something because it's 3x3. So in the GRU and LSTM, you can see these weight matrices, they're conserved. Why? Because we use them over every time step. Right? Every input, every word, every character, every whatever thing you're feeding in is using the same W matrix, right? Same W matrix. That means every time state you're using the same WZ, same WR, same big W, whatever, the one without any underscore. You're using these 3 learn matrices that could be pretty big. It depends on the dimensionality of your input, right? If you're using natural language, your dimensionality of your input is usually what? How big is it? No, not 100K. What's the dimensionality of the input that you feed in?
Number of possible characters? So
it could be. But what do we do with language that you've heard a couple of times? There's a one word that I'm looking for. It starts with an E. Yes, embedding, right? You stick the words, you stick the characters, and you make it an embedding. And Jeremy hinted a long time ago that you can do this with any categorical variable, right? You just map it into an embedding structure. You get a number of dimensions. It's up to you. Again, if you want to play a little bit more conservative because you don't have enough data, you set the dimensions to a higher or lower number. Lower number, right? Lower number means you don't need so much data, right? So in embeddings, you've already seen many times how many dimensions you have: 150, 250, 300. Right? Because they think the words have enough semantics to be preserved in 300 real numbers, whatever. It seems to work empirically, right? I hate that word, but yeah, that's what we use right now because we don't know any better. Okay? So that means all of these matrices have at least one dimension that's 300 in size. Okay? And another dimension, I'm not quite sure what it is, but if you know, you can say. Okay? But it's being applied at every time step, right? So it doesn't matter how long the input is, right? You're just applying these 3 matrices for the GRU, 2 matrices for the LSTM, 4 matrices for the sorry, 4 matrices for the LSTM, 2 for the RNN. Okay. Okay, go ahead.
Okay. So previously we already talked a lot about CNN. So today I'll just like concentrate on some of the interesting concepts in CNN. And first, let me briefly introduce some of the basic concepts in CNN. The first one is depth, namely the number of filters being used in processing a picture. And strat is the sets which we select the filter. The strat is like when we apply a filter, like how large a step we take when we use a filter to like process an image. And zero padding is we like artificially add a lot of zeros around the border.
You should draw it.
You can go ahead.
Okay.
Let's just continue.
So we can imagine if we use a filter whose set is not 1, if we don't do any zero padding, when we try to like process the image, the sets of the image will become smaller and smaller because like when we apply the filter at the edge, actually, yeah, the size of filter makes it cannot like maintain the size of the original image. And the other reason why we should use zero padding is like the pixel at the corner, they're like not adequately dealt with because, for example, when we use a 3x3 filter for a normal pixel inside a picture, it will be like dealt with for 9 times, but for pixel at, for example, at the left bottom corner, it will only be applied to a filter for 1 time, which means that this is the idea, which means that we are likely to lose some of the information inside pictures. So it's crucial under certain circumstances to apply zero padding. You see it, yeah.
So for example, here like this pixel will only be counted here, so it will be counted like 1, 2, 3 times. But if we don't use the zero padding, then this pixel will only be once. But the pixels that are in the center, so for example, here, it will be used once, like 9 times. So you have a much more importance. But in the corner, it will just be used once. We cannot lose some information. This is a zero padding, then we add a few more occurrences, so we keep more information. And also, when you use the filter, it will reduce the size of the original picture each time. So,
okay, next. This is an illustration of the concepts I just taught in the previous slides. And in this example, we use a number of filters of 2 and the strat is 2. So when the size of filter is 3 and strat is 2, when we apply such a filter to a picture of size of 7 times 7, we will get an output volume of 3 times 3. There's actually a formula for this, but it's not very difficult to get. So yeah, I didn't put the formula here. Yeah, so basically we have like 3 dimensions, which may mean like red and blue and yellow or something. And we apply different the first set of filters, actually it's the same filter but for different colors, and we apply those 3 different sub filters into those 3 dimensionalities, and then we like add the value up. Because we are applying 2 filters, we will get 2 output volumes. Yeah. And another concept we use CNN is max pooling, which is very simple to understand. We just like extract the max value of each like sub-region of the original picture. For example, in this example, we extract the max value of the 2 times 2 rate. Yeah. And another approach for the pooling is average pooling. where in which we don't take the max value, instead we take the average value. We can imagine if we take the average value, the picture will be like become more blurry, and if we take max pooling, the picture will be like more sharp. I don't know whether they are like the whether they are the right word I use, but yeah, you can imagine what happens if in the red picture the number is not the max but the average. Practically speaking, max pooling performs better than average pooling, and maybe because it can maintain more features from the original, like original picture. Yeah. Maybe you can. Yeah, anybody wants to add anything?
Between the max pooling and the average pooling, we're not sure like why it performs better with the max pooling.
Okay, great question for the floor. Why does max pooling work better than average pooling? He did say something about this many lectures ago. You've watched the lectures, right? Just because it's online and you can watch anytime doesn't mean you watched them right before the final. Don't worry, there's no final.
So we thought that is because the average, so it's kind of like blurring the image. It's just like the mean, so you don't get like the extreme. But if you just have the max, I don't know if like the minimum also makes the same thing as the max.
Okay.
Is it because the boundaries get you can like resolve the boundaries more clearly in max pooling?
No.
I think it's because you choose like the strongest activation in each region. So like, yeah, it's just you just choose the most prominent thing inside each region.
Why would we want to do that though? That's a very good point. That's the correct answer. But why is that the right?
It's the E word.
The E word meaning
Empirical.
empirical. Yeah, the cursed E word. No, it's actually due to something else. Okay, so Jeremy explained this. I'll try to explain it again. All right. He said when you're looking at an image, okay, looking at an image of cats, all right, when you go through this image, right, you have the red region, the green region, the yellow region, and the yellow region. Think of each of those pixels, the number there as the signal to say, how confident am I that there's a cat there? Okay, if you average that, you get an average number. If you maximize that, you're saying that there's at least one pixel here that's pretty sure there's a cat here. Okay, and so even though the rest of the pixels nearby don't exactly look so cat-like, there's a good chance that there's a cat because at least one part is sure. Okay, so that's the idea of using a max pool. For example, if you have an image of a person and they're partially occluded, right? Partially occluded, which means what? An average will just say, probably there's no human there, right? Because you cut half of their face, okay? But somewhere in that image, there was a particular segment where the filter said, there's an eyeball there, I'm pretty darn sure, okay? I'm gonna fire that there's an eyeball there. And then the larger detector said, that looks like a face because I was quite sure there was an eyeball there because the max pool told me that there was an eyeball there. And someone else told me that there was a mouth below, okay? And I'm gonna for sure fire that I'm pretty confident there's a face, even though the other eyeball is missing, okay, whatever. Okay, that is the purpose of max pool. Okay, if you average pool, you're going to lose it. You won't be able to find it. Okay, if you use the E word, you're right. You won't be able to detect it, but you need to know why. Okay, that is the reason why. Okay, because for a lot of times when you do recognition or classification, there are certain signals that need to be present. Okay, if they are present, then you fire. You say, I'm pretty sure that's what I heard. Or, I'm pretty sure that's what was meant, okay? And if other signals don't quite help reinforce it, that's okay. Think about sentiment analysis, as we talked about last week, right? You see the word happy, I'm pretty sure it's a positive sentence, okay? All the other things in the sentence like school, homework, those are all negative, right? Who likes school anyways? I mean, you guys signed up for permanent head damage, okay? But because of that, you know, you have a lot of slightly negative words in the sentence, but you heard the word happy. That's a positive word. You fire on that. You don't fire on the rest. Okay? So there are lots of consequences of using a max pool. All right, that's one of them.
But you will not have like more false positive, like for example, if you have the word happy, but that's sarcasm, then you fire it's positive, but actually it was just a sarcasm because you say, yeah, I'm very happy to be at school, then it's like a false positive. Or like if you see that you have a leg, you think, oh, that's a human, but actually it's I don't know, it's a monkey. I don't know. I just say something. Do you have like more false positive? Use max Q.
You might, yeah, you might. I wouldn't be too surprised if you have people wearing cat masks, okay, and they get fired as cats, right? I don't know, okay. And it's true that we have other architectures to partially do with some of those problems like polarity in sentiment analysis. You say not happy, the not is negating the happy, right? And so an LSTM or other sequential architecture would be able to say, there's a sequence of words here. I saw not, and that means something is going to change with the word after that, right? So we can model that. It takes a certain network architecture, but the general idea of max pooling is that people are very good at paying attention to certain details, right? We know from human vision, you may not be paying attention to something, but suddenly there's a movement on this peripheral side of your vision. You notice that. Why? Because it somehow triggers, your innate primate sense of danger, right? You need to know what's happening in your environment, otherwise you'll be eat or be eaten, right? So that was the premise of computer vision a long time ago. Is living things evolve the ability to move, and when things can move and forage and find things, then they also need the ability to know when they're being foraged for, right? So movement became important. Okay, so those are some of the underpinnings of why we use max pooling. Okay, it's two things, right? One is because we think that a positive activation should be passed up, and average activation may not be so important for exactly the reasons I said. An eyeball should be a very positive feature of a face. Okay, skin tone, that's an average feature. We are not going to fire on skin tone. There are plenty of things that are skin tone, so things like that. Okay, but an eyeball is a very firm recognition. Okay, second thing is resolution, right? That's the pooling part. So do you guys want to discuss pooling? So we already discussed the max part of the operation. Why is it max? Why is it not min? I like min, I'm min, but that won't help. But why not average? You guys know that now, right? Okay, how about pooling? What's the importance of pooling?
Reduction of dimensionality.
Reduction of dimensionality. So how does that help?
You have more noise in your signal.
It will take the important features of the image, capture all the important, and highlight those information necessary.
So both of you are right. There are a couple of considerations here, right? Pooling helps to get rid of the noise, like you said, right? So when you do max pooling, you end up with only the positive activations that are most prominent, okay? But because you're reducing the dimensionality of your data set, your filters at the higher level are applying over a larger resolution space, right? So you've seen these diagrams before where the 3x3 filter on the bottom layer is only looking at 3x3 pixels. But when you go to the second layer, level 1, not level 0, how many pixels is a 3x3 looking at? If you fed it through a max pool before you went to the second level of doing a convolution, a 3x3 convolution.
Four times.
Half.
Suppose the max pooling is 2x2, right? Then the second layer you will look at 4 times 3x2.
Mm-hmm. So you can do it on this diagram, right? Right. So let's say we have this max pool, right? So we're getting a single number from here, a single number from here, a single number from here, a single number from here. All right. So these 4 numbers are coming over a 4x4 grid, right? Right. Right. So all of these are right. Sorry. Where am I? Here. Oh, let's take it in the middle somewhere where there's no Okay, so these four. Okay, then it is 4 by 4, right? It's this one. Okay, so we have these 4, and then we do max pool, right? So then I'm just taking, let's say, one set of numbers from this thing. So I'm getting one number here. So this area is being reduced to a single number here. Okay. And if I do max pool on these 4, then I'm getting a single number, right? And I continue, right? So let's say I have
stride.
one, two, three,
Sorry?
4, 5, 6,
You
7,
forgot
8,
stride.
9, right? Because I'm doing 3 by
Stride.
3 convolutions. This other one would come from, right?
So
it comes half.
Right?
so just one.
Wouldn't this
Do you
become
make
like
a stride?
The stretch to
Stripes is one.
Yeah, we haven't talked about stride yet. I guess you guys are going to talk about stride.
Ah.
No?
I thought about it already.
Oh, we talked about it.
Yeah.
Okay, good. Okay, so I'm doing a stride of 2 because I don't want to overlap.
Yeah.
I didn't tell you that, so okay. So then, what resolution is this 3 by 3 filter going? Right, if I have a view matrix that's 3 by 3. Right, let's say this is one of our filters.
half the resolution.
Right. So if I map this 3 by 3 length, right, I'm actually doing it over all the way over here, right?
Oh yeah.
So 1, 2, 3, 4, 5, 6, 7. Right. So my 3 by 3 at the second level here, after I've done max pooling, I had a max pooling somewhere in there. Okay. Then I get a 7 by 7 using a 3 by 3. Right? What does that allow me to do? It allows me to see bigger faces. Right? Because this one is looking for faces or whatever feature it is at the 3 by 3 pixel level. Right? Now I'm looking, maybe I have the same W matrix as here, usually not. But then I'm looking for features that are at the 7 by 7 level. Right? And if I do it again, right? Let's say I do this max pooling and then hidden convolution later. Okay. Again, then I'm doing it over a wire field. Right? So that's why many times you need to have a different set of W's at every level because you're looking for features that are more and more coarse-grained. You go back to that AlexNet or I think the BTG paper, ImageNet one, where they show you all the pictures of the activation maps, right? You see at the basic level, they're looking for like, I don't know, edges, roundedness, gradients, right? And then it gets higher. You look at textures, you look at like organic shapes, right? Because they're higher in resolutions. You wouldn't be able to see a lot of those types of features at a very 3 by 3 pixel level, right? Can you imagine looking in your I don't know, your Apple iPhone or your Samsung S8, just take any 5 by 5 image pixel crop. Well, you see nothing, right? You gotta be kidding me. You have to look at least at 50 pixels to see any useful features that would denote an object.
Okay, the next concept I'll be talking about is batch norm. Yeah, don't be scared because of the formulas. Actually, the idea is quite easy. We maintain a mean of the vectors input as 0, and we kind of like control mean and variance. Yeah, and let me explain this to. Sorry.
Why they add the error term when normalizing? Normalizing is done basically by taking the subtraction of a mean divided by the standard deviation.
You mean
in the third formula?
The third formula?
Yeah. Why they are adding the error term in the denominator?
So boy divided by 0 something.
I think so. Yeah.
Yeah, it's
I think so. Yeah.
The number to be too small, so they're adding this number. We explain this in the video.
Which part? Epsilon?
The third formula.
The denominator, there's this epsilon. Yeah, so the problem is actually to avoid the number to be too small or to be big.
Okay. So yeah, let me explain this doodle. So when you train a model, when the input comes like again and again, originally the input, but you don't know what will happen if you take into like more input. Maybe it will appear at some unwanted positions, and the idea is that we need to like somehow control the scale and the position of the input in like a holistic way, so that this graph becomes the distribution will be closer to the origin point. And because we are going to like control variance, so the scale of the data won't be very large. So this is like the basic idea of professional. So yeah, the benefit one is what I just mentioned. We need to like somehow control vector, because if in the training process, what we apply to a vector is identity matrix, then that would be like ideal, because we are pretty sure that the data will not grow too large or too small as a snowball, but that is like very unlikely to happen. So by using background, we are somehow like control the sets of the data. And benefit to is to introduce noise, because we are kind of like changing the meaning of the data input. So in such a sense, we are like deliberately adding some unwanted elements inside the training process, which is quite similar to dropout. We are like trying to prevent the problem of overfitting.
Did everybody understand it?
I understand why this.
Because if we are trying to substitute the original data with those things, the new xi, and in this process we are like changing the original meaning of the data. Because only if we fit into like we input the original data, like the training will be like ideally the optimal, but that will generate the problem of overfitting. So it's kind of like artificially input some of the noises.
So does like really small numbers become zero or something?
No, like really small.
Because your number is computed based on the
yes.
information in the new number and the information in the old number should be same. Right? You didn't lose any information.
I didn't lose any information, but like I changed some of the data. Yeah.
But you got squashed it all the way.
Mean is lost. Mean is lost. So that way you consider it to be some sort of noise.
Yes.
Does everyone follow that argument?
Yeah. So if the number is like close to zero, then it will become larger.
Oh.
Because we need to like maintain variance as one. Yeah.
The purpose is actually avoiding explosion or vanishing.
Oh.
Yeah. Otherwise, it will be like either your data will be smaller and smaller and smaller during the training process. Later, Jiang will talk about like the detection of object in the ResNet part. So I'll just give a brief intuition of how it works. So in the training, we just describe the detection of object as a long vector, and the parameter is like something that we can choose. But normally, there will be a Boolean value telling you whether an object exists or not, and some of the values will be describing the position of the object. For example, the right corner, left corner, those kind of things, like denoting the square surrounding the object. And some of the values will also be Boolean, denoting the classification of like what object it is. So if he like input all the information into a vector, it won't be. It depends on the size of the classification. So for example, if we have 4 elements describing the position and we have 3 classes, in this case we'll have like 8 elements, like final output. Yeah. And for those kind of more complicated tasks, we just say we need to, in the training side, we need to like manually input all the position of the crucial point on a person's face. And the final vector will be also larger. Like it will definitely include all the x coordinate and y coordinates of the key points on a person's face. Yeah. And this.
Can you go back to that?
Yeah. Last one, I think this.
No. Yeah. What do you mean by manually input all the coordinates? You mean somebody has to label all the individual points here?
As the training set, yeah.
As the training set.
Yeah.
So you're basically saying this is more difficult problem because the cost of training set is also much more. Because you have to do all this.
It's not a more difficult problem. It's just like time consuming. Yeah. Yes. Because it's a whole repetition one.
I thought most people just use bounding boxes for detection of objects. Is it?
Because
they ask people to tag, the left bottom and the top right. But you're saying in this particular case, you have to label all the coordinates of the center of the eye, the eyebrow, the bridge of the nose.
But for like objects like cars, we don't really need a very detailed description of like which part of car we are describing. But for example, face recognition, we need like all the crucial points on the face.
For face recognition, or
it's like a very.
I can still recognize a face without knowing exactly where the eye is. I think you mean if you're trying to do something with the face, like lip reading or emotion detection, then I need to know whether I'm scowling or I'm happy, right? But for a camera to know that there's a face there, I think it only needs to know the bounding box, right?
No.
Would you say that? No, it needs to know the entire face.
Just for face recognition, I don't think you need this detailed description.
Right. So that's what I'm thinking, that when you label the detection of objects, maybe you mean the specific objects here, like the nose, the eyes, the eyebrow, the lip.
Yeah, this one is
not the entire object of the face, right?
No.
Yeah, okay.
This one is definitely for some like more complicated tasks. For example, like motion detection or like matching whether like 2 people are the same person.
Okay.
Yeah.
Yeah. Now the phones and the laptops has this authentication login using the face recognition. So the face recognition, is it following this authentication, right? You can unlock your computer by just looking to the camera. Right?
I would rather believe it's more of using this, because all you need to do is like to tell whether it's a face or not, instead of like describing the detail, like the position of nose and stuff.
No, actually, it's much like the second one.
Really?
Yeah. Yeah, and I'll tell you why. I mean, you can go to Tuesday night class here in SOC. Terrence, my neighbor, also teaches bio-authentication. So he covered a part where he asked the class whether they have iPhones and use the iPhone 10, right? X, whatever it's called, that has the facial recognition. So the problem with face detection means anyone can unlock your phone. I just need a face to be there.
Oh, yeah, that's true. That's true.
Oh, that wouldn't be very helpful. I need to know it's your face and not someone else's face, right? So in the biometric case, you have a lot of false types of problems, right? You have type 1 errors, which means it doesn't recognize your face. So you can't even use your own phone, which is really annoying. Or much worse than that is type 2 errors, where somebody picks up your phone and can access your bank account I'm sure you would prefer that you get slightly annoyed with your phone when it doesn't recognize your face, right? And maybe it says you must go wash your face is dirty, whatever. Okay, have a good cleanliness, hygiene routine, whatever. But the important point is that those types of errors are quite different in the authentication scenario, right? So you cannot falsely authenticate someone. If my student or my son picks up my phone, you know, he's a younger version of me with his mother's genes as well, he shouldn't be able to use my phone, right? And buy all the expensive toys he wants to get on Amazon, okay? So that's important. So definitely, if you're talking about facial recognition for authentication purposes, yes, you're right, it has to be much more complicated, yeah.
Like with Apple thing, they have introduced a 3D thing.
Yes.
That improved. Like initially, they used to take a print of the photo and then you used to, but that thing doesn't happen. People try it many times.
Yeah, so you can't take somebody's picture and then present it to the camera and hope to authenticate. You have to have a 3D model, or the depth, basically the Microsoft Connect that they put into the Apple iPhone.
Tried also that also. Create a 3D and put it on the face. That also.
Yeah.
How do they do 3D? Is it that they just take consecutively two images, let's say, part of a 0.1 seconds, and then
they created the face structure of someone.
Oh.
But the image captured by the camera is always 2D. Like how?
No.
It's
a
The
3D.
first time you register for your Face ID is actually you have to move your head like this.
Yeah, so you move your head. So you have to move your head. So you take two pictures at slightly different angles.
So, I mean, the iPhone 10 has two cameras, and it also has an infrared camera or something in between.
Yeah.
Okay, you've heard of Microsoft Connect, right?
Yeah.
This software, hardware device that you can use to play games and things like that. They basically took a Microsoft Connect and miniaturized it into the iPhone.
Yeah.
So that basically is the same thing that you have in the iPhone. It can detect gesture, detect pose and recognition, detect your face to a fairly high degree of accuracy. It has some problems. I heard it works well in low light, so you can authenticate your face even in darkness because it has an IR sensor. Okay.
It also radiates something on your face too.
Yeah, so maybe in 10 years you'll be a little bit like darker because of all the radiation that's coming out of your phone.
Yeah, and this is just an extension of what I talked about in the like. So this one you like combine all the vectors in like every subgrade, and if the original vector is of the set 9, then this one will be 9 times the number of cells to kind of detect multiple objects. Or yeah. So I'll pass my time to Ding Feng, who will be talking about residual network.
Okay. Hello, I'm Ding Feng. I'll be talking about ResNets, and we don't have much time left. So is everyone familiar with ResNets? Like, you all know what it is? Okay. So I'll just go a bit into the motivations of why they use ResNets. So like, what happens is when you have like you stack a bunch of layers on top of one another, and like the moment it gets really, really deep, the gradients cannot propagate back properly, like it vanishes or something. So like the training error and the test error increases. So the thing about this is that it's somewhat, well, paradoxical, because with more layers, you're supposed to do better, but it doesn't because of vanishing gradients. So so what they did to, also in like 2015, a miracle happened. So someone invented the ResNet, and it just wiped the entire competition away. It's like around 152 layers, much deeper than whatever we have seen before. So this is really amazing. So how they did this, the trick about what this ResNet is, this res stands for residual. So this residual is, you can think of it as like the stuff that's remaining. So what you do is you propagate whatever your input is, the X at the bottom, you push it up, and you take the difference
and you get your 2 layers in the center to train to fit that difference. So what the 2 middle layers are learning is they're learning the difference between what is expected and the difference between what is expected and what is the input. So you have to what the 2 middle layers are learning are just the really small differences, the delta x. So well, for some reason it performs much better, and you can propagate the gradients much deeper this way. The suggested reason that they have is that because of this skip connections just somehow passes the information directly, and your middle layers are just learning these micro steps of the differences, just learning how much to add to each layer to make it look like the next one that you need. So this is a lot less complex than trying to approximate the real answer, like trying to recreate the real answer. So what you're doing is trying to add on to the original answer that you already have, instead of trying to recreate the entire thing. So that's the hypothesis. Whether it's real or not, I have no idea. Yeah, this is the same thing. It's just comparing what a classical layer is like against a residual layer. Okay, so like they have lots of this standard ResNets around. So this ResNet 50, 101, 152 means how many blocks of ResNets you stack on top of one another. Just standard models. So each ResNet in itself is a block. Inside would have 2 convolution layers and probably 1 batch norm at the back. I'll go more into it later. Okay, this part. Okay, this one. Like if you look over here, this is what the inside of a ResNet looks like. So this basic block is the ResNet with one convolution, another one, and a batch norm at the back. Oh yeah, so you stack a bunch of these together and you get your neural net. Okay. Oh, another thing that Jeremy talked about was something called class activation maps. So there's a bunch of code that he did to try to pick out the kernels that the features of where the cats are and overlay it as a heat map on the picture of your cats. So how this is useful is that he said that perhaps when you have a really large picture like 5,000 pixels or something, 5 by 5, yeah, you can run the neural net once on the entire picture, and like you get points of interest, crop them out, and rerun the thing on them again, or do some data processing to improve your output. Yeah, this is a bunch of code, something special. Like you can read it. Oh, okay, and we have come to the end. Yay! Any questions? Anyone?
2 slides ago.
Okay.
The graph, why does the error rate drop drastically? 50 and 60 people.
30 and 60. Jeff. Sorry. I'm just trying to demonstrate the because there's some naming conventions to what this 50, 101, and 152. Like yeah. This?
Yeah, so ResNet 50 is.
Number of layers.
Oh, 50 blocks. Oh, it's 50 layers. Alright, oh sorry. Yeah, it's 50 layers.
So I think the point they were trying to make is that with this kind of architecture where you just take the residual part and you just propagate you just find the difference between x and the edge of it. The depth of the network will not matter. You can see that all of them have comparable performance.
Yeah, like they said that Jeremy said that this idea of skip connections is, well, somewhat applicable to everywhere. So you could try throwing this into like LSTMs or something. I did say something about some LSTM network that uses this skip connection idea and got better performance. But yeah, I forgot what it is.
But after 60 epochs, you are getting that error rate very less for others.
For this, is it?
Yeah.
Error rate is less than others.
Yeah. So ResNet basically saturated at that point.
Yes.
And, I'm trying to make sense out of it.
Oh.
Are these the older architectures?
Yeah, I think these are older architectures. They are performing better when epochs are. They are performing worse when the epoch is less than 30, and they are performing better when epoch is greater than 60. Yeah.
So I think when you can't go on for so many epochs, ResNets are.
No, what? Nothing here.
Because I think I read somewhere that so the point of comparing ResNet 50, 101, and 152 is that because you're using these skip connections, you can start like removing layers in the middle.
Oh. That makes sense.
So because you kind of like just train over the differences will end up working. I don't know, something like that. And like you don't need your dependence on each of the layers is reduced. So if you reduce the number of layers, the performance doesn't.
Oh.
Okay, so I put some more links on the Slack. You're welcome to check them out. I think it's good to understand what the residual network is doing and why that architecture seems to work, especially for larger networks. That's the key thing. It's like when you go to a larger network, you have, a deeper network rather, you have more problems with backpropagation and gradients. So you need to mitigate that to a certain extent. So the tutorial that was written by, given by the person at Microsoft who actually created the system is quite useful. But the summaries on Quora and Stack Exchange are always the best place to start. Then you can go back and presentations in the Okay. With that, please make sure you fill in your information on the Google Doc if you haven't already. I need that by this afternoon. Okay, so I can send the emails to you. And then for those of you finishing your lab rotation 1, good luck with your next lab rotation. Hope we'll still see you on Friday mornings. Okay, that's it. Thank you.
Thank you.
Okay, so my group has its own research group meeting right now. So we'll see the rest of you at Steps or next week.